So first, we have Tévécia Ronzon. I don't remember where you are from, but I know you're great. We met before. So introduce yourself.
Then I will introduce myself. I'm Tévécia Ronzon, and I work for the JRC, as many other colleagues here. The JRC is the Joint Research Center of the European Commission, and we are based in Seville. Today, I will comment on those dynamics of bioeconomy development, but mostly in the European Union. So I think this will provide a complement to those presentations we had yesterday on Northern America and Latin America. I will look at dynamics at the macro-regional level, the EU level, and then I will go down to countries, industries, and markets. And the last part of my presentation will focus on a study we've elaborated at the JRC and with biomonitor partners on the progress towards the bioeconomy transition in Europe. So this is not big news because it has already mentioned several times during this conference. We are now celebrating a decade of bioeconomy strategy at the European Union level. What is a decade? 10 years is at the same time very short to bring about a paradigm shift, but it's long enough to start or to kick off transformation. And this, during that decade, so we have been quite busy policy agenda of monitoring, revising, updating the strategy according to an evolutive policy context. There have been a lot of funds dedicated to the bioeconomy, and most of them went to research and development because in Europe, the bioeconomy derived from R&I policies. So those funds have been directed to research through framework program, and the Horizon 2020 is one of them. It founded the Biomonitor project. During the new program financial period, it has been replaced by Horizon Europe. But there have also been funds directed directly to the bio-based industries through public-private partnership. And this is not trivial because 1 billion euro has been channeled to this public-private partnership in the last financial period, co-financed with more than 1 billion euros from private origin. And this will be repeated in the new financial period. So we are speaking about really big amounts of money. Also, the classical financial instruments have been mobilized towards the bioeconomy in Europe. The European Investment Bank and the European Investment Funds have created dedicated schemes for the bioeconomy. And part of the resources we are earning from the emission trading system in Europe goes to these innovation funds that will finance investment in low carbon technologies and bioenergies. Then more classical policy instruments have also been adapted, and I'm thinking about the new CAP, in which there are dedicated measures to support the bioeconomy in rural territories. And of course, because the European strategy has a strong environmental component, also funding is going through environmental measures for the preservation of natural resources and biodiversity at the same time that we are using more and more those natural resources. So this is for the macro level. Now, what's happening at the national level? You will see on these slides two maps. The one on the left represents the situation in 2018 and the one on the right, the situation in 2020. So only 4 years time span. And in green appears those countries which have a national bio strategy in place or that are developing their own one. And in only 4 years, you can see that the map is going green, meaning that at the policy level, there is quite an engagement towards the bioeconomy. And I think this is really interesting if we compare with the presentations of yesterday, where we could see that in Northern and Latin America, which are hugely endowed with biomass, the bioeconomy is not developing too much through federal or national strategies. But in Europe, where biomass is so limited, there is this policy push. So I don't know if this is related, but we have very distinct dynamics going on. So that was for the policy level. Now, what's happening in reality? Here, the JRC has mapped bio-based plants. There are more than 2,600 bio-based plants mapped all over Europe, of which 500 plus corresponds to this definition of a biorefinery, which would be a bio-based plants that produce multiple products from biomass feedstock or bio-waste or biogenic in general feedstock. So we can say first that yes, biorefinery are developing across Europe, but their development is very uneven. If you look at the south part of Europe and the eastern parts of Europe, the density is much, much smaller. And this has triggered more dedicated support to, I'm thinking, the Bio-East region, for example, in order to try to catch up in that aspect. Now, what's happening on the markets? I'm using here input from the Biomonitor project, and I will focus more on the bio-based chemical markets, which is quite strategic in the European Union. Here, colleagues from Biomonitor have quantified the production of bio-based chemicals in the EU. And you can see that since 2012, the launch of the first bioeconomy strategy in Europe, the domestic production has going up, which can be considered as a success of the strategy. And the main categories of chemical products that are produced in Europe are liquid biofuels, chemical platform products, surfactant, and cosmetics. Now let's go more in details, and this is still inputs coming from the Biomonitor project. I wanted to mention here the case of bio-based polymers for plastics, because there are also a lot of strategic policies behind. We can see that in this case, if you look at the red and the green line, we can consider as quite a success. Both the use and the domestic production of bio-based polymers for plastics has been growing in Europe. So yes, the industry is engaging towards more bio-based feedstock, and yes, they are also trying to provide those feedstock by domestic production. And now, if you look at the bottom part of the graph, second success is that this gap between import and export is reducing over time, meaning that the European Union is also gaining more self-sufficiency. But now, if we look at the biggest producers in Europe are Italy, Germany, and then the United Kingdom, which is sadly not a member state anymore, for those bio-based polymers for plastics. Sorry. Now, if we look at another strategic market for bio-based chemicals in Europe, the one of bio-based chemical platform products, the story is a bit different. On the one side, yes, the green line is growing, meaning that bio-based industries are using more and more bio-based chemical platform products, which was one of the aim of the bioeconomy strategy. But the red line, the production, domestic production, is not keeping the pace, meaning that our dependence to import is dramatically growing in Europe. So this is something we have to be aware of by monitoring these markets. In Europe, the biggest producers are Germany, the Netherlands, and Italy, and maybe we need some more effort on that market. Okay, so that was for the main dynamics. Now I would like to present the results of a study we've conducted in order to quantify progress towards the bioeconomy transition at the EU level and in member states. And in that study, we started with two main assumptions. There were that bioeconomy transition would occur if we modernize our bio-based industries and if new bio-based value chains emerge. And those two phenomena will have an impact on the overall level of labor productivity of the total bioeconomy. So first, before quantifying those two phenomena, we had to quantify the total level of labor productivity, which appears on the y-axis of this graph, with the arrows showing the different position of the member states from 2008 to 2019. First, very positive message. All arrows are pointing up, meaning that the labor productivity has increased in all bioeconomies across Europe, except for Greece, which is the exception. Second message, the arrows are much, much larger in those member states represented in red and orange, northern and western member states, than in those member states represented in purple and green, meaning that most of the labor productivity improvements has occurred in Western and Northern Europe. Also, we can see that over the 10 periods analyzed, none of the purple and green member states have reached a level of productivity above the EU average. So it appears like if there were a glass ceiling at the EU level that divides Europe into big parts. So now, next question was, okay, so we can say that there are member states where the transition was more successful. Let's try to understand what happened there. And we were able to quantify those two phenomena thanks to a shift share analysis by quantifying how much labor productivity gains come from the within effect, effort of raising productivity in industries, and how much was coming from a shift of workers from old industry to new ones in the bioeconomy. And this is shown in this graph with the within effect on the x-axis and the between effect on the y-axis. Because there is this little window, you cannot see the 4 very front runners in Europe. 2 are hidden, but those are Ireland, Denmark, Belgium, and Finland. Yes, thank you. We can consider that in those 4 member states, the transition has really advanced because they were able to perform at the same time very large intra-industry labor productivity gain, this within effect, modernizing their bioeconomy industries. And at the same time, also structural changes in the sense that they developed bio-based industries that were more productive than the old one. Austria occupies an intermediary position, unless the other northern and western member states were not so advanced in the transition, in the sense that, yes, they did operate some intra-industry improvement, but they did not operate any structural changes. And the situation is even less advanced, let's say, in Eastern and Central member states, where labor productivity gains were much more moderate, maybe with the exception of Portugal and Poland, where they are starting to operate structural changes. And now I will finish with a last consideration. We will go back again to those 4 front runners, Ireland, Belgium, Denmark, and Finland, where then we asked ourselves, okay, they were champions of the bioeconomy transition. What were the industries that were leading this transition? And here you can see those 4. One moment. Those 4 member states with, again, this within effect on the x-axis and between effect on the y-axis, and the size of the cycle represents the net effect. So very quickly, we could observe that in 3 of those member states, bio-based pharmaceutical industry was driving the transition, with both structural changes operated and intra-industry gains. It was followed by the manufacture of food and agriculture. I'm going quick. And that Finland has a very different profile, probably because he's very well endowed with forests. In Finland, another transition pathways was developed with forestry leading, both in terms of modernization and attraction and development of the industry. And this probably triggered also the modernization of the manufacture of wood and paper that are downstream the forestry activities. And I will just conclude with this wrap up. The bioeconomy has reached European policy agendas, both at the macro level and national level. There are signs of industrial uptakes, but the transition can take different pathways and is heterogeneously advanced across countries and sectors. And I will have no time to speak about this last point.
We'll have questions later on. Thank you. Now, the second speaker is Justus.
Right, while the slides are uploaded. So my contribution will be more on the methodological side. And if you have listened to what David has said this morning, right, we should invest a little bit more time in thinking about methodological issues and not only looking into empirical issues. And that is what I like to point out in my presentation. I just put here up the motto of Wageningen University, that is to explore the potential of nature to improve the quality of life. So the bioeconomy basically plays a very important role within the university from all its different dimensions. What I will concentrate here, as I said, it's more on the methodological side, is how do we address issues that are related to future development, and how can we get a decent understanding about how we on first hand should value these developments, and secondly, what might be the implications of policies on the potential developments. And here's some basic assumptions that we normally have in our models, but they are very important to restate here. We often assume that assets can be traded, so we have markets for buyers and sellers. That is a very important issue to consider. We also have to consider, and that has been pointed out by Rich Saxon, right? Information arrives over time. We live it's difficult to forecast how the future will be. All the macroeconomic models show a distribution of outcomes. And that applies then for decision makers, whether at policy level or at private sector level as well. They have to deal with this. Now, if you assume that we have a model that is arbitrage free, and normally that is what we do as economists, then basically one can show that this implies risk neutral probabilities. And when we look at risk, we have to consider that risk in general normally would not pose a problem if we can easily reverse, right? The problem with risk comes if it's irreversible. We observe that the situation is not as we expected, and we cannot move back costlessly to the initial state. So that's why it's not the risk itself that is relevant, it's the irreversibility costs that are related to this. Now, what is it? Now I have to come to a definition, and that is irreversibility effect, because there are some different definitions and use of concepts in the literature. So the way I use the irreversibility effect, that is additional reversible net benefits have to be larger than one to compensate for 1 unit of irreversible costs with respect to immediate investment. So that is my definition of the irreversibility effect. Now, there are 2 important things that we need to consider when we look at this. And sometimes it's drives me a little bit nuts that in many papers, I observe that they do not consider that if we have changes with respect to risk, that has an effect on immediate values as well as future valuation of our investments. So we will have an effect on the current investment costs and benefits and the future investment costs and benefits. And these 2 effects have to be taken into account. And this has then, if we have a model that is relevant, and with relevance, I mean that it may pay to wait, because in the future there might be the chance that the investment may not pay off. That is a very important assumption that has to hold to make the models interesting. And then if we look at the results of this very simple model, discrete time, discrete state, and look at marginal change effects on either benefits are high or low, what we will then observe is that the marginal effect on change in the lower part of the benefits has a much larger effect on the investment decision than if you look at the higher level of benefits. Now, we use these models and apply them to a number of economic situations that are of relevance. And our basic structure that we are using is we say, okay, we have for investments R&D phase, The R&D phase is uncertain in length. Everybody, I think, who has done research will confirm this. Then we have, depending on where you are, an approval phase that can be larger, that can be smaller. But the approval phase length is also uncertain. And everybody who is here in the audience and has done something with approval of new technologies will also confirm this. Also, industry is very much complaining about exactly this approval phase, where it takes a long period of time to get the things ready for being able to be sold on the market. And then we have what we call the marketing phase, a phase where you can sell your products on the market. Well, this marketing depends not only on the time length that you have, but also on the market size that you have. And the market size that you have is dependent on the approval that where you get the products be approved for. And then we have as a large component there, that is what we call ex post liability, that within your market, you may face the risk that you will be held liable even you have gone through the approval process. And I tell you, Bayer will tell you the story and confirm this, that this ex post liability can be a very expensive thing to come. And we have to include this in the models as well for proper policy analysis. Now, these phases are uncertain in time, and if you then develop a real option model around this with uncertainty about the future and uncertainty with respect to the time length, then we can solve this model. I just show you the equations that we are able to do this. But what is interesting here is that if we solve this model and normalize the effects of time length to 1, and then run simulations over different possible time lengths, over different rates of discounts, over different ranges of probabilities, then we observe, for example, that here on the phase for R&D, that if you have 1 more year in R&D research to be phased, the threshold value that you need to reach increases by 70%. So you go up from, let's say, 1.2 to 1.9. We observe the same if you run the simulations, for example, for the approval phase. Of course, ex post liability. If you have a policy that poses more an ex post liability, the further the ex post liabilities in the future, that has a negative effect. So basically it has a positive effect on the investment hurdle. Now what this demonstrates here is that in particular, we get the highest coefficient for the approval phase, that policies that either extend this approval phase extremely increase the disincentives for the private sector to invest. If you have policies that reduce the approval length, you have substantial incentives for the private sector to go into investment. It also confirms why the private sector is very much complaining about this approval length, because it's an extreme hurdle. And well, to illustrate why this is relevant not only for one sector policy, this here is a figure that shows the interaction of the European bioeconomy, the flow of value added around the different sectors, and that is basically related to the results that Tévécia has shown, is that if you regulate in one area, this has indirect effects also on the other areas in our value chains. And that implies if you have strong regulations in the GMO area, this has indirect implications for the other sectors within the bioeconomy. And that is what we need to take into considerations as well. And if we, for example, then look into the farm to fork strategy of the European Union and assess what are the implications of the proposed farm to fork policies. And I have to confirm what Robert Mbarek said. This 25% organic agriculture, that is a policy statement, right? So it's not mandatory in the sense that the countries have to do that. Now here comes a but. But the member states have to submit their common agriculture policies to the European Commission. And they have to indicate to what extent they are complying with the farm to fork strategy. So it becomes an indirect, basically, policy objective. Now, if we look at the implications of the farm to fork strategy with models that just apply continuous growth rates derived from the past without extra additional technological change, except for what we have had in the past. Then if we look, for example, at the land use, at the climate change effect, and that is one of the main objectives of the farm to fork strategy as part of the Green Deal, to reduce greenhouse gas emissions. If we include leakage effect and land use change and forestry effects, the balance is negative in the sense that it increases greenhouse gas emissions. At least this is what the model shows that has been done by colleagues from Kiel. Now, I'm almost done. There is a possibility, and that is another study that looked into what are the contributions that plant biotechnology breeding can contribute, and that is here in this figure. The dark green bars show the negative welfare effects, and the green ones show that if you would introduce genome editing, to what extent that can compensate for the negative welfare effect, ceteris paribus. And just to illustrate here, we have done a number of studies that are confirming that this really matters. So to conclude, we have to consider two effects if we go into policy analysis, and that is consider the irreversibility effect, and that means to identify reversible and irreversible benefits and costs and consider that risk is asymmetry. I strongly propose that we have to put more attention to this. We also have to consider that timing is state dependent. So when we try to estimate what would be the optimal time for a policy change from today's perspective, that doesn't tell us so much. Next year, the situation may be completely different. And regulatory environment, they have a strong effect on investment, and institutional change for technical change is extremely important to get or to moderate, for example, the potential implications of the farm to fork strategy. Thank you very much for your attention.
I'm really pleased to have Tassos Xapadeas. Tassos was the president of the European Association of Environmental Economists. He's an incredibly prominent environmental economist. He's a member of the US National Academy of Science, and it's a big honor for us to have him here. Tassos, the floor is yours.
Thank you, David, and thanks to the organizers for inviting me. It's a great pleasure for me to be here. It's a great honor to present my work. What I'm going to present you in the next 15 minutes, I hope, it's a theoretical model. It's a conceptual model, which is part of an ongoing research with a good friend, a colleague of mine, Bas Brock from the University of Wisconsin. And the idea here is to try and explore in a qualitative way, ways to design policy which are efficient according to our criteria. So I don't have numbers, I don't have data. There are lots of equations in this paper, which I will keep it to an absolute minimum. But the idea is to provide some indication for policy design, and I think that some of these policy implications are in line with what we are discussing here. So let me, I need this. Okay. So let me start with COVID. The idea is the COVID crisis, apart from all the measures that we took to control the epidemic, also brought in the discussion about how we deal with pandemics and whether there are long-run drivers that might affect the possibility and the intensity of having new diseases emerging. So this is the idea. I took this graph from epidemiologists, and here they sort of try to describe the different aspects that affect the emergence of the disease. here is the human factor. And for the human factor, we decided to analyze two issues: the impact of humans to climate change and changes in land use, and the way that these human impacts here go back and affect the emergence of a disease. Now, the way that we looked at the problem, in two time frames: a short-run time frame and a long-run time frame. Now, in the short run, the idea is that the COVID is here, and all we try to do is try to control it and eliminate it. But in the long run, what I think is important is to try to understand which are the drivers that might affect the emergence and the intensity of this disease, and whether we can do for these long-run drivers. And the drivers that we choose to analyze is basically the natural world. And I'll try to explain what I mean by that, and of course, climate change. So we try to find evidence that link these long-term drivers to the emergence of the diseases. Now, I found this quote from Jane Goodall, the well-famous anthropologist, that basically says that the emergence of COVID is due to overexploitation of the natural world. Forest cut, species made extinct, and so on. There is another quote from a paper that is coming out in the annual reviews of resource economics, David knows the paper, by a group of researchers in Stanford. And the important thing here is that they observe that activities that led to anthropogenic disturbance of the environment, primarily climate change, land use change, urbanization, and so on, affect the emergence and the intensity of infectious diseases. And look at these graphs, this from the same paper. Here is the temperature and the disease transmission. And here is the other graph is rainfall and disease transmission. And these again indicate that link, that there's a link here. What I found more interesting is this graph. And this graph describes the changes in the land use and the link of these changes with different types of virus. And you see that I guess we're somewhere here in the industrial agriculture, and these are related to the emergence of different virus. Another aspect that we found even more interesting is the link of this famous R0 of the infectious disease, which basically person infected per person infecting, okay, how many persons an infected person might infect. And here is from the same group of people, the link between temperature and R0 for these three types of infectious diseases. And final evidence comes from the graph about the valley fever. And here we have a link between the expansion of valley fever and temperature. And again, the idea is that as we experience climate change and global warming, these might be regarded as long-term drivers in terms of diseases. So this is the idea. Now, what we tried to do was to try and build these ideas into a model with an economy. As economists, we experienced and we developed these integrated assessment models to study climate change, starting from Nordhaus and the famous DICE model that eventually provided the Nobel Prize. The idea is to have two modules, to have the economy on one side, climate on the other side, describe the links: economy generates emissions, emissions change climate, climate generates damages, and so on and so on. And these are the famous integrated assessment model. The idea now is to try and develop what us and other people call an EPI-ECON model, integrated assessment model, that will also include into the whole model a module that relates to an infectious disease. So this is the whole idea. So the idea is to develop the model and the module that we try to put in the economy is a very simple infected susceptible model, an SIS model, which is very standard. It's very standard in epidemiology. There's no deaths in this model, just to make it more simple. And what we try to do in this model is to make the contact number, which is the important number about the way that the disease is spread, to make it dependent on policy instruments. And we describe two types of policy instruments. In the short run, we try to control the disease by vaccinations, lockdowns, and other issues. But in the long run, and this is something that actually it's a policy proposal, in the long run, we should try to control the drivers by affecting changes in land use and climate change. This is the whole idea. Let me just give you one equation here. This is basically the policy-dependent contact number. S, we should try to push S towards 1. S is the proportion of susceptible in a population, which means those that are not affected. So we want S to go close to 1. And these are the two parts of the number. This is the long run part, which depends on the natural world, what we don't use in agriculture or urbanization, and this is temperature. Okay? And the other is the short run part, which basically depends on what controls we take, vaccinations, and so on. This is some other factors here, number of susceptibles which are infected but are asymptomatic, and they affect the contact number. And here is we decided to split the world in two regions, the tropics and the north. And here is the movement of people from one region to the other that might also affect the contact number. So this is our policy. From the part of the economy, what we try to do is to assume that there is consumption good that we all want to consume, and this is produced by labor, energy, and land. And we split land in two parts. I mean, this is a conceptual model, so might not fit exactly what we understand in terms of reality, but we split land, agricultural land, in two parts. One is traditional agriculture, and the other is what I would call high-tech agriculture. High-tech agriculture could be part of what we're discussing here, high-tech technologies that increase productivity. So labor is offered and is used to produce the consumption good. Infected people cannot work. So when we have infection, we reduce output. So if we try to control infection, we increase output, and this is good. And of course, we have costs. We have costs to produce energy. Energy has dual characteristic. Energy is good because it produces good, but it's bad because it accumulates greenhouse gases and brings climate change. We also have damages from climate change, and all these things we try to put them into the model. The other part of this model, what we add in the model, is innovation. Innovation is related to high-tech, what we call in abstract terms, high-tech agriculture, and it acts as land augmented, if you want to use the word, technical change, which means that this part of innovation affects agricultural land and increases productivity. It's basically what we're discussing here. This is obtained by knowledge accumulation, but again, knowledge accumulation is costly. So the whole thing is to try to control the system, in a sense, to try and see what kind of policy implication we might extract by considering a model like that, a model that contains all the ingredients that I just described, and what kind of policies we might want to discuss. Since we split the world into two parts, our solution concept is Nash equilibrium. The idea here is that the two regions, especially in terms of policies related to health, have their own policies. So they describe independently about policies, trying to obtain the best for each region. So in economics, the standard solution concept in this context is a concept of a Nash equilibrium. So we're looking for a Nash equilibrium within this model, and we try to understand what kind of policy implication this Nash equilibrium context has. Now, as I said, we split the model in two parts, short run and long run. In the short run, we deal with controls and policies that will contain the infection, and we regard the longer-term drivers as fixed. So first, we solve the problem in the short run. In the long run, which is the model I put there, what we try to do would be to optimize over an infinite time horizon. You saw lots of infinities when Justus did his presentation. Here I had just one infinity there. And the idea is to try and optimize this criteria that consists of consumption here, and here is the natural world, which are that it's taken to reflect existent values and ecosystem services related in this natural world. Now, the constraints of the problem, here is fixed land, which is allocated to one type of agriculture, the other type of agriculture, and the left is remained as the natural world. Here is the evolution of the greenhouse gases, emissions from one region, emissions from the other, and some kind of depreciation of greenhouse gases. This is a standard way of modeling these accumulations. Temperature is linear to the accumulating greenhouse gases. This is the latest approach in climate science, this linearity. And here is the accumulation of knowledge. Knowledge is accumulated and then promotes technology in high-tech agriculture, promotes increased productivity. This is the whole thing. This is an optimal control model. Is solved. I won't bother you with the solution. I just wanted to describe the model. And then basically, what we try to do, we try to derive policy implications by making some simplifying assumptions that will make the model tractable. And the idea here is to create, to link the solution of the model with the concept of the natural world and the concept of climate change, and get some kind of policy implication out of that, which I will try to show them to you in a second. What we found the most interesting policy implication is that in the solution, okay, when economists try to value ecosystems, they have a concept of total economic value that puts use values, non-use values, existence values, and then we try to estimate these values, sometimes by using market data, but we don't have market data. We try to elicit reference from people by asking them, using contingent evaluation methods, using experiments, and so on. What comes out of this exercise is that another value emerges at the solution, and this relates to the value that we attach to the natural world as a way to stop, or if you want to reduce, the intensity of an infectious diseases. So I would say that in a contingent evaluation study, one, apart from asking different attributes associated to the natural system, also one must try to ask willingness to pay to reduce intensity of infectious diseases. And this might be important in actual cost-benefit analysis because it might affect the way that you value conversion versus development. Another characteristic of this type of value is basically it promotes this idea that by increasing the productivity of agricultural land, you save natural world, and this is good not just for climate change, but also it's good in terms of these infectious diseases. Actually, this is the last graph I will show you. It comes out of the solution of the model and basically shows that if this n equals 1 is the solution of the model without innovation. As innovation goes through, this frontier there shifts to the red triangle, and at the solution it can be seen that as we shift the triangle, the natural world increases. So basically we conserve, and this is also important for climate change. So just to sum up, I think within a few time limits, two policy implications coming out of this model. The first is that in contingent evaluation exercises, we might ask willingness to pay to reduce the intensity of emerging or possibly emerging infectious diseases, and how we're much willing to pay to do that by conserving the natural world. And also, something that also came out is that the social cost of carbon that Christian Gollier was discussing the other time increases again because climate change, temperature increase might also increase the intensity and the probability of having an emerging disease. So again, one value of CO2 that is saved, that is not emitted, might worth more because of this second effect. And I will stop here.